going. There we go. This is made of, hydrogen is made of 2 atoms. Yes, 2 hydrogen atoms make that molecule. Do you know what word we use to show that hydrogen is made of 2 atoms? Starts with a D. Diatomic, yes. Because we have 2, which is di, and then atoms, which is atomic. And so hydrogen is a diatomic element. In nature, it comes in little partners. Fluorine is also a diatomic molecule. And what does this single line represent? That is a single covalent bond. How many electron pairs are in that single covalent bond? 1 electron pair. So that's 2 electrons in total, but we usually count them as pairs. So 1 electron pair. Okay, good. So fluorine is very similar. When we get to something like the next one, which is carbon dioxide, we have a little problem because carbon has 1, 2, 3, 4 holes. Yes? And oxygen has 1, 2 holes. So we're going to have to do something a little bit differently. Okay, we're going to have the carbon share 2 of its electrons with the 1 oxygen and 2 of its electrons with the other oxygen. And don't worry too much about figuring out how you know that, okay? What you should be able to do is you should be able to look at that structure and say, is that structure okay? Does everybody have 8 electrons? So, does oxygen have 8 electrons? 1, 2, 3, 4, 5, 6, 7, 8. Yes, it does. Does carbon have 8 electrons? 1, 2, 3, 4, 5, 6, 7, 8. Yes, it does. Okay. Once you get to grade 10 and 11, you'll start doing a little bit more, figuring out how many of each thing have to go with how many of each thing. But, oh, and we have here, how would we draw a structure like this for a carbon dioxide molecule? On one side, we have an O, and then we have a C, and then we have an O. Yes, in that order. What should I draw in between the O and the C? Chat with your partner. What should I draw in between the O and the C? Bless you. Anyone? 2 lines. And the same thing over here, 2 lines. So that is a double covalent bond. How many electron pairs are in a double covalent bond? 2. 2 electron pairs. And the nice thing is that Oh, never mind. I was going to say something, but it's not true, so I won't say it. And then finally, down at the bottom of the page, we have carbon and fluorine. But you'll notice that fluorine only has one unpaired electron, right? So it can only share one electron, but carbon has 4 holes, yes? So how many fluorines will you need to fill up those 4 holes? You'll need 4, right? So you've got 1 electron from, oh, that was supposed to be highlighter. It didn't show that way. You got 1 here, 1 here, 1 here, and 1 here. Okay? And this is a molecule, and it is of a compound called carbon tetrafluoride. Tetra meaning 4. Here is a definition of a molecule. A molecule is an electrically neutral group of 2 or more non-metal atoms held together by covalent bonds. So there are actually 4 parts to that definition. Number 1, it's electrically neutral. Number 2, there are 2 or more atoms. Number 3, those atoms have to all be nonmetals. And number 4, they are covalent bonds. We are on page 45. Do you have your book, Jack? Why does a formula unit not qualify as a molecule? Now, first of all, what is a formula unit? Do you remember? It's a single unit of an ionic compound. So we just defined molecule, and we said there's 4 parts to that definition. Do you have a pencil? Do you need one? So why does a formula unit not qualify as a molecule? Can you see anything in that definition of a molecule that does not work if we have a formula unit? Chat amongst yourselves, see if you can come up with some reasons why a formula unit does not qualify as a molecule. And Rajan just told me this one. What does a formula unit have in it that a molecule does not? It has a metal, yes? So it's a metal plus a non-metal. Anyone come up with a different one? Yeah. Yeah, a formula unit is for an ionic compound, not for a covalent compound. So, and I can't abbreviate formula unit because it's rude, so we won't do that. A formula unit, I know, right? I'm like, okay, what do we abbreviate it as? We can't. Okay, we'll just leave it there. A formula unit is for an ionic compound. The bond is an ionic bond, not a covalent bond. Anyone want to add anything else? Okay, so we're going to go to the next page and we're going to see if we missed anything. Okay, so we'll just give you a minute to finish that down, and then we will carry on. Okay, so did we get, let's see, here is a formula unit. There's our crystal lattice. Number one, did we get the first one? A formula unit contains both metal and non-metal molecules, are made exclusively of non-metals. So we got that one, yay. Ionic bonding is the kind of bonding in the formula unit, so we got that one. Okay, whereas covalent bonding is for a molecule. Here's another one. A formula unit is made of oppositely charged ions. So the formula unit is made of ions, whereas molecules are made of neutral atoms. Here, I'll go back and color code these. Molecules are nonmetals. There we go. And here's our last one, and this is kind of an interesting one. A formula unit never actually exists on its own. It is always a part of a larger crystal lattice, whereas molecules can and do exist on their own. You can have a single water molecule. When you boil water, each water molecule is separate from each other in the air, okay? So the number of holes in the valence shell. What is valence shell? Outer shell. Generally determines the number of bonds. There are exceptions to this, but we won't learn them this year, okay? So we have carbon. How many holes in the carbon atom in its outer shell? 4. 1, 2, 3, 4. And we have also hydrogen. Now remember, hydrogen only has a single shell. How many holes in the hydrogen atom? How many electrons do we need to make hydrogen full? Only one, because remember that first shell only needs 2 electrons to be full. So carbon has 4 holes, so it's going to have 4 bonds. Okay, and so what the bond is going to look like then is we're going to have the hydrogen atom come and share its electron. We will have a second hydrogen atom come and share its electron. A third one. And a fourth one. And that's lovely because now carbon has how many electrons in its outer shell? 1, 2, 3, 4, 5, 6, 7, 8. How many electrons does each hydrogen have in its outer shell? 2. So is everybody happy? Yes, they are. How would we draw this is called a structural diagram. So if I put carbon here, and I put my hydrogen here, and here, and here, and here, what would I draw in between the hydrogens and the carbons? I would draw lines, and each line represents how many electrons? 2 electrons. Each line is 2 electrons. Okay, and if we were to write the formula for that, how would we write the formula for that compound? We would write C, and then what? H4. Yep, CH4. And if you are interested in doing the black diamond kind of stuff, the name of that compound is methane. The prefix meth means 1 carbon. So anytime you hear the prefix meth, it means there is a single carbon. Okay? So methanol is a 1 carbon alcohol. And it's not the kind of alcohol that you would ever want to drink because it would make you go blind. Okay? So there's all kinds of different alcohols. You know, like in the drugstore, you can get rubbing alcohol, right? That's also not a kind of alcohol that you would want to drink. Quite frankly, having done some research on what actually happens to the brain and to the liver and to everything else, probably you should never drink regular alcohol either, but I know that's an unreasonable expectation to put on everybody. But the longer you can put it off in terms of your brain development, the better. Your brain is developing all the way up until you are 25 years old, okay? So the longer you can put it off, the better for your brain, the better for your liver. If you do drink, it's so much better if you don't binge drink, so do a whole bunch, because that causes the most damage, right? So, you know, the French, they have a glass of wine with dinner, every day. You don't see them, dying quick deaths. It's when you have that sort of really awful, overload, because it is a toxin. Did you guys know that alcohol is also a carcinogen? What is a carcinogen? A carcinogen causes cancer. Yeah, alcohol is a carcinogen. It also causes heart disease. So just as a public service announcement, the less, the better. Yes? Okay. Anyway, meth means 1 carbon. Someone in my morning block was like, does that mean that meth, like crystal meth or whatever, has 1 carbon? And my guess is that the actual name is methamphetamine. And so there's a complicated amphetamine molecule, and then there's a little 1 carbon group sticking off the end of it. Okay? Yeah. I probably could, although to be honest, it's been a lot of years since I've done organic chemistry. So there's a lot of complicated glassware, and you have to get the temperatures right, and you have to do things that's called reflux, where it boils and then it goes back around and down. And it's literally been about 30 years since I've done any of that. How do I know what? I'm guessing, because that's how a lot of organic chemistry labs are done. Yeah? I'm just trying to remember what I did 30 years ago in organic chem lab. Yeah? You could. However, it's not harm-free, which I think is more important than tax-free. Okay? Like that's a really super destructive way to make your living. Okay, anyway, that is methane. Now we have nitrogen. Nitrogen is in group 15. How many valence electrons if it's in group 15? 5. Okay, so how many holes does it have? 3 holes. 1, 2, 3. So how many bonds will nitrogen form? 3 bonds. 3 holes. 3 bonds. Okay, so over here we go. Here's our hydrogen. Here's our hydrogen. Here's our hydrogen. Hydrogen, hydrogen, hydrogen. How would we draw the structural formula for that, the one that has all the lines in it? How would we draw the structural formula for that, the one with the lines in it? We put an H and then what? A line and then an N and then a line and then an H. And then down at the bottom we would have another line and then an H. Okay, and if we were actually doing this in grade 10, you would even put your lone pair of electrons that are not bonding electrons up top like that. Cool, hey? You don't need to know how to do that. Okay, so I'll get rid of that. Okay, so that is NH3, and its name, oh, NH3, here we go. Oh, sorry, NH3. And its name is, again, this is black diamond stuff, ammonia. Anyone heard of ammonia? Yeah, it's in P. It's also in Windex. It's often used for cleaning. So if you get that smell from Windex, that is ammonia. Okay? Ammonium and ammonia. Oh, okay. So ammonia is a chemical. Oh, that's okay. No worries. That's pneumonia. They're not related to each other at all. Okay, so pneumonia is like when you get a bacterial infection in your lungs. Okay, or actually sometimes it can be a fungal infection or a viral infection. There's viral pneumonia, bacterial pneumonia, and fungal pneumonia. But basically it just means you get a lot of fluid buildup in your lungs and it's really hard to get rid of. Okay? So one is a disease and one is a chemical. All right? So we have ammonia, and then our last one we're going to look at is if we have oxygen. Oxygen is group 16. How many electrons in valence electrons in oxygen? 6. So how many holes? 2. 1, 2. So how many bonds? 2 holes. 2 bonds. Yep, so we would have 1 bond here. What happened? I wanted red. There we go. Okay, there we go. The structural formula, HO, and it actually doesn't matter whether you put it out the side or whether you put it at the bottom. I'm going to put it at the bottom, but it doesn't matter. You could also write it as HOH. And the formula is, of course, H2O. And what is its Name water. That is not a black diamond. You should know that that is the formula for water, okay? So the next page is just in there in case you were like, you know, away and didn't fill it in with us. I should really put it in the answer key rather than in the booklet, but you know, there we are. I'll do that for next year. Put in answer key. Okay. Now, multiple bonds, double and triple bonds. In a double bond, how many shared pairs of electrons? So in a double bond, how many shared pairs of electrons do we have? We have 2. In a triple bond, the number of shared pairs is 3. Okay. So for some molecules, the sharing of 2 electrons is not sufficient to fill the outer shell. So let's consider the series of F2, O2, and N2. We start with a fluorine atom. We add to it another fluorine atom. And when we combine the two, they become a fluorine molecule. What type of molecule is fluorine? F2. That is a diatomic. Okay, now if you're wondering why are some of the electrons circles and why are some of the electrons X's? The reason is that it is easier to see which electron came from which atom. Yes? So we have the left hand fluorine and we have the right hand fluorine, and we can see that one electron came from here and the other electron came from the other atom. Yes? And so you can see there's one from each. So it just allows you to know who the starting atom was that gave that there. And of course, here we have that one line there. That is our single bond. That is one pair of electrons. Oxygen. Now, if we look at oxygen, how many holes in oxygen? 2 holes, right? So each oxygen needs somebody to share 2 electrons with them, yes? To fill up those holes. And so each oxygen will share 2 with its neighbor, okay? And we end up with those bonding electrons there. And if you see, each oxygen now has 1, 2, 3, 4, 5, 6, 7, 8. And the other oxygen has 1, 2, 3, 4, and then the shared ones 5, 6, 7, 8. And so we show that as a 2 lines. That is our double bond there. Okay. What would I put in the boxes above those things? I would put oxygen. What's this one here? That's an oxygen atom. Yeah. And the symbol for that would be O. We have another oxygen atom, and the symbol for that would be O. And then we have an oxygen molecule, yes. And the symbol for that would be O2, yes. And you'll notice, remember when we said the number of holes is the number of bonds, right? 2 holes, 2 bonds. So we have 1, 2 bonds is a double bond. Yes? I just put a fresh battery in you. What are you complaining about? Okay. And finally, we have a nitrogen what? A nitrogen atom and another nitrogen atom. And they get together and they form a nitrogen molecule. The symbol for the nitrogen atom, of course, would be N. The other one would also be N. And how about our nitrogen molecule? N2, which means what kind of a element is it? It is a, if it's got a little 2 at the bottom, diatomic, okay? Never goes around without its little partner. And how many holes in nitrogen? 3, 1, 2, 3. So they have to share 3 electrons with each other, which means if we have 3 holes, how many bonds do we have? 3. So we've got 1 pair, 2 pairs, 3 pairs. That gives us our triple bond there. Okay? Which is the strongest, a single bond, a double bond, or a triple bond? Triple bond. If you don't remember from last day, we looked at this and we were like, oh, look, oh my gosh, it's like there's 1, 2, 3, 4, 5, 6 ropes pulling these towards the center, whereas with only 4 electrons, there's only 4 ropes pulling it towards, so it's just not as strong. Okay? If you want to read this next page, you can. I'm not going to go through it though. We're going to carry on to the next page. Even though this is a black diamond, I'm going to just show you a couple things because I think it's really interesting. Most of the time, covalent bonds result in molecules. This here looks like a molecule, does it not? Yeah? This kind of looks like a molecule, yes? However, sometimes, not often, but sometimes you can have covalent bonds extending through an entire network that goes on and on and on. Very similar to how an ionic crystal lattice goes on and on and on. So for example, you will end up with many of these silicon and oxygen, silicon dioxide, that end up making sand, okay? And you can have a large grain of sand and you can have a small grain of sand. And so the size of that structure depends on how many of those units are repeating over and over and over. Now, we have a couple of models here. Here's carbon. What group is carbon in? Carbon isn't in group 14. So how many valence electrons? 4. So how many holes? 4. How many bonds? 4. Watch this. Here's a carbon atom. It's bonded to one carbon atom, 2, 3, 4. It makes like a little tripod kind of structure, yes? So every carbon atom is bonded by a very strong covalent bond to 4 other carbon atoms. This form of carbon, super, super strong, super, super hard. This is diamond. Okay? So that would be what you would see if you had diamond. But we all know, at least I hope we know, maybe we don't all know, diamond is not the only form of carbon. Can you guys think of where you might find carbon in this classroom? In your pencils. Okay, so in your pencil, the graphite is made of carbon. And this is what carbon looks like when it is in graphite mode. And graphite comes in sheets of this honeycomb-like structure. So you have these little hexagon honeycombs, and you have layers of them. So there's in this one, there's 1 layer, 2 layers, 3 layers. Yes? It looks like the carbon is only bonded to 1, 2, 3 things. Yes? 1, 2, 3. In between the layers, these aren't actually bonds. It's just that there's no way that this structure would stay together if we didn't have a stick between them. Yes? So these are covalent bonds. In between the layers, there are much weaker forces. Okay, those weaker forces are called intermolecular forces. They are forces between intermolecules, intermolecular. So there's these weak forces in between the layers. But within the layer, there's these really strong bonds. And if anyone's wondering, hey, I thought you said carbon had 4 holes, why are there only 1, 2, 3 bonds? It's because this model is not perfect. One of these 3 bonds should be a double bond, which would give you, if this one was the double bond, it would give you 1, 2, and then 3, 4. Yes? Now, why is this so amazing as a pencil? Well, not only are there these weak forces that stick the layers to one another, so you can imagine, if you've got within the layer, these atoms are stuck together like they're stuck with super glue, okay? So that's a really strong bond within the layer, within that hexagonal sheet. In between the layers, it's like they're stuck together with peanut butter, okay? It sticks them together, but if you start moving it, it's going to slide, yes? Now, there's also peanut butter on the outside here, okay? So when I take my pencil, and now this is going to be my pencil because it contains the graphite, okay? And I start to have it right on the table, okay? There's going to be forces between the table and this bottom layer. And if we press down, it's going to shear off and pull off a layer and leave the other layers behind. Yeah? And then because these layers are so thin, even though the bonds are quite strong, you can still snap it because it's so thin. Yes? So that will just snap off, and that's how a pencil works. So this layer here would then be off on the page. Of course, there's a lot more layers than 3, but that's the general idea. And I wanted to show you that because I thought it was cool, even though you don't need to know about that for grade 9. Okay? So those structures where you have this great big thing, for those of you who are interested in the enriched stuff, those are called covalent network solids. Okay, so here you can see we have diamond, We have graphite, you can see very distinctively here. We have the sheets in which there are the covalent bonds. Between the carbon atoms. And then in between the layers, we have weak forces. Hold the layers together. Okay. There we go. Is that it? Might be it. So there's your graphite, there's your pencil. Very nice. If you're interested in what those weak forces are called, these are called intermolecular forces. And if you take grade 11 chemistry, those will become very important to you. And because that's such a great big word, we often abbreviate them as IMFs. And they are relatively weak. Okay. And I think that's it for this one. We're just going to do a little bit more, and then I'm going to give you some time to work on homework. So let's see where we're at. Dot and cross diagrams. Yes, this is what we want to do. This is on page 50, is that a 60? 64. Page 64. So a dot and cross diagram is a way to show the arrangement of the outer shell electrons. And we've been doing some of that already, but this time we're going to formalize it by using dots for one atom and crosses for the electrons of the other atom. Okay? And one nice thing is that in a dot and cross diagram, often we don't worry about the inner shell electrons. We don't worry about those core electrons. We only draw the valence shell. So you don't have to be drawing, 3 circles if you've got 3 shells. You just draw the outer shell, which is kind of nice. We also don't worry about how many protons and neutrons are in the nucleus. We just write the element symbol in the nucleus. Okay? So we often only the outer electrons, and the charge of the ion is spread evenly, and we do that we show that we'd have that using brackets. And remember, you're going to have brackets, and you're also, when you have brackets, you're going to put the charge. Yes? Only if you have an ion. So in ionic bonding, Who gives the electrons and who takes the electrons? Tell your partner. Who are the electron givers? Who are the electron takers? Yeah, so the metal transfers the electrons to the nonmetal. So the metal is the giver. The electron giver. And the nonmetal is the electron taker. When we show the process of the formation of an ionic bond, so this is showing ionic bond formation. One of the things that we need to do is we need to actually show the movement of the electron. Okay, so you use an arrow to say, oh, look, this electron is moving over to the empty hole in the chlorine, and it ends up over here. Okay? So you draw your atom, you draw your atom, you show the electron movement, and then you show an arrow saying, oh, this is what it turns into. And don't forget, once it has lost its electron and it takes on a charge, you need the brackets and the charge. Yes, because sodium is now positive and chloride is now negative. What would be the name of this compound? Sodium chloride, yes. Would it be okay to write the formula like this? Is that okay? We don't write charges in the formula. When you have an ion on its own, you write the charge, but once it's in a compound, you do not write the charge, okay? Here's another one. We have magnesium and we have oxygen. And you'll notice that oxygen has two holes. You don't have to draw the holes, that's not a requirement, okay? Sometimes I like to, just so I know where things are going. So oxygen has two holes, and the nice thing about magnesium is that it has two electrons that it would like to get rid of. Yes, so we show the arrow, okay? So we need to show those arrows showing the movement of the electrons, and then we show that our electrons have, ooh, that's not good. The electrons have moved to their new place. Because oxygen gained two electrons, it is two negative, so we need to put the brackets and the charge. Magnesium is two positive, brackets and the charge. What would the name of this compound be? MgO. Magnesium, yes. Oxide. Now, sometimes, up till now, it's been very nice. Somebody needed 1 electron, the other guy had 1 electron. Somebody needed 2 electrons, the other guy had 2 electrons, yes? However, look at this down here. We have calcium would like to get rid of 2 electrons. If we had only 1 fluorine, that would only take care of 1 of the electrons, yes? So in order to satisfy calcium, we need another place for an electron to go, and so we need another fluorine, which also has only 1 hole, yes? And so it can give it to another fluorine atom. And that's why the formula for calcium fluoride is CaF2, because you need 2 fluorines to satisfy calcium giving away its 2 electrons, okay? And you could draw it like this, and that would be calcium. And I want you to watch out for the spelling of fluoride. F-L what? U, fluoride. Okay, so calcium fluoride. Watch out for this. Fluoride, right? Not fluoride. Okay, but fluoride. The U comes first. Flu. So those are your ionic compounds. That's how you show the formation of ionic bonds. Now we're going to take a very, very quick look at forming covalent bonds, and then we will give you some time to do your homework. And you might not even have homework over the weekend if you work really hard. Okay, but you still got 3 days to do it, so it should be good. So we are trying to get a noble gas electron configuration. What does it mean to have a noble gas electron configuration? Noble gases always have a full valence shell. Okay, yes, of course. Which is also known as a complete octet. And the only time we don't have an octet is when we have something like hydrogen, okay, because hydrogen only has 1 shell, so how many electrons does it need? 2, okay, but most of them need 8. So when we're drawing the formation of a covalent bond, we start by drawing the 2 atoms. So we have an atom, and we have the other atom, and you'll notice one of them has X's and one of them has dots, even though they're both hydrogen. And then we have an arrow. And then we show an area of overlap, and we put the bonding electrons go in that area of overlap. Kind of, it's like a Venn diagram. Yeah, very much so. Okay, so we've got HH, H2, hydrogen molecule. One shared pair of electrons means we have a single bond. Yes, Alvin? Do they have to look different? For these particular diagrams, yes, because it shows that you know from whence they came. Yes, you know that one came from the right hand and one came from the left hand one. Okay. Okay, and again, we have an atom, and we have an atom, and each of them has one little gap. Yes. And so again, we show the arrow, and then we have the area of overlap. And here we have how many pairs of shared electrons? How many pairs? One pair of shared electrons. So is that a single, double, or triple bond? That is a single bond. Excellent. And then if you want a bit more of a challenge, you could try something that has a double bond, because you can see oxygen has two little gaps and it has two little gaps. And so you would need to actually share all four of those. So in this case, we would have two pairs of shared electrons, and that is a double bond. And finally, nitrogen has three holes, so we need to have three bonds. And if it's bonding with nitrogen, they might as well just share all three of them. And that is a triple bond. Okie dokie. How come this class always seems so much shorter than my other block? Because we had like 15 minutes to do our homework in the other block, and you guys have like 5. And I'm like, why? Why? I don't feel like I'm talking slower. Like, I really don't. I don't understand. I think time moves differently in the afternoon. So I'm going to give you your homework, which unfortunately you don't have as much time as I wanted you to have to do it, but you can try and get a little start on it. The homework is page 39, 19, 53, and 54. I know it sounds like a lot. It's not actually that much, and you have 3 days. Come on, you can do it, okay? And because our test is maybe next week, at the end of the week, you're going to add to your vocab list. Maybe. Well, I don't know. I'm thinking maybe the test will have to move to the following Monday. Your blog. We're putting them off until I say so, okay? So no blogs until I say so, okay? So just ignore them for now, okay? We'll maybe do some more like later in May and June, but for now I want to get through some curriculum. Okay, you need to come and show me any homework that you've done right now. None. Okay, so I'm going to write down everything you need to do, okay? Hi. You can, yes. Okay, so don't go away. You need, if you could bring me your book so I can put this sticky note on the front. Okay. No, go bring it for me. We'll bring it, yeah. And Jack, you need to come by and do corrections on your test. Because right now,